Good afternoon, everybody, and welcome to this webinar where we'll be looking at modeling and designing castellated beams in IDEA StatiCa. My name is Jacobus Oberholster. I'm an AEC and Procon technical consultant with Micrographics, and you will also see my email address in the bottom left of the screen. So you are, of course, more than welcome to reach out after the webinar if you have any questions, if you'd like access to the models I'm using. I'll happily share those with you. Um, and yeah, so we do have a live chat. You're welcome to post any questions you might have in the live chat as we go through the webinar. I would really recommend doing so rather than waiting for a dedicated Q&A time. If I can't answer your question, I'll do my best to reach out to you. Or otherwise, what I would ask is that if I can't answer your question at the moment, then I would ask you to please send me an email with your question so that I can get back to you and give you the appropriate answer. So, without further ado, let's jump into our agenda for this webinar. So, of course, we've gone through our little introduction. We will look at what castellated beams are and their benefits. We'll look at typical approaches to design and their limitations. We'll look at, of course, the focus of this webinar, the modeling of castellated beams in IDEA StatiCa. We'll look at the analysis and design within the IDEA StatiCa space as well. And then lastly, we'll just have a conclusion. So what is often the case with the webinars that I present is that we tend to have a massive practical component so that it keeps us engaged, because we don't want to sit staring at a screen with just a ton of information, written information being thrown at us. So we'll discuss these points as we work through our modeling in IDEA StatiCa itself. So there won't be dedicated slides discussing these specific points. All right, so let's jump into IDEA StatiCa. And what we've got here is, of course, are the range of modules, and we will be looking at the member module. So this is specifically member for steel, because there's also member for the concrete side as well. So let's look at member. Just something I'd like to mention as well is that because this is live, whenever I run a design or analysis, we actually have to wait for it to conclude in real time. So please just bear with me as I work through all of these workflows. What I do want to show you is just what is possible within the member module. So I've got castellated beams with purlins. So I'm going to open that up and just show you what that looks like. We're not going to model to that specific depth just because it really takes a little bit of time to get here. So here you can see our castellated beams, and there we've got our purlins also with their plates running in the lateral direction. We've got our haunches and we've got our apex as well. And we'll just discuss the significance of these features as we work through. And you'll see why I am showing you these members or this particular model over here. All right, but this is already run. You can see, unfortunately, the linear buckling analysis output has been cut off here. So we'll just have to run that. But this one has run successfully, which means that it is seen as a solid model. Okay, so I'm going to close this, and then I'm going to start a model from scratch where we're going to look at modeling our castellated beams and so forth. Like I mentioned just now, we're not going to model in those purlins just because that adds quite a bit of time to our modeling, but I'm going to go to new, and I'm going to start from scratch here. All right, so we want to give this a project name. You have to actually give this a project name. So I'll call this castellated beams for MGFX, and I want to make sure that we are in the correct folder. All right, we're happily there. We can set our steel grade, our design code. Unfortunately, the South African codes have not yet been programmed into IDEA StatiCa, but the Euro codes are applicable in the South African context, fortunately. We've got a steel grade, a weld grade, and then our concrete grade, if that would have been relevant. So here we have these options. So I'm going to click on this geometry here, and I'm going to look at the cross section. I'm not going to care too much about now. I'm going to modify that within the model itself. But what we want to do is we actually want to create some additional nodes. All right, so we've got node 1 on this side and node 2 over here. So I'm going to add a Z value, so 1.5. I'm going to add an additional node at X is 16. And then here, there's actually something quite important. So beginning and end node is like this. So this is node 1, that's node 2. And on this side, we'll say the beginning node is node 3 and the end node is node 2. That order is incredibly important because once you start adding operations to your members, that order will affect the side from which the operation starts. And we want it to start at the column side of these rafters. Okay, so that convention really is important versus saying that the end node is node 2 and the beginning node is node 2 and the end node is node 3. We want them to share a common end node. All right, and with that, I'm going to click on Create Project. So the first thing we'll do once the project is created, we're going to leave these loads here by now. They are just there by default. We can, of course, delete them, so that's not a problem. But we want to now create our castellated beams. So I'm going to click on AM1, which is this beam over here. You can see the cross section over there. And I'm going to click on the little Add New. And this is not a generic section. So of course I have to go to welded and composed, and I'm going to go to IW to do this. Okay, my name is going to be based on some convention that works for me, and we'll look at that shortly. And I am going to look at a 686 by 191 by 98 castellated beam. So that has got an original I section of 457 by 191 by 98. And this is all in accordance with the red book. So HC is the new height of the section, which will be 696. Then we've got the flange thickness is 19.6. And the width of the flange is 192.8. Our web thickness is 11.4, and then that's about it. So my convention is going to be CUB, so that can be Castellated Universal Beam, and I'm going to give it its new designation. All right, and then one thing I would want to do as well, because of a limitation in the member module, is to check whether or not my flanges or my web are considered class 4 elements in bending. All right, so there's different limits for an inner element in axial compression versus bending. And if you look at those limits, you'll actually see that the class 4 limit is 10.61 for flanges for both compression and bending. Whereas for your webs, it's 35.56 for compression and 100.8 in bending. Now, why am I mentioning this is when it comes to castellated beams, your web to, let's say, height ratio, because that's technically what it is, or the web thickness to height ratio of the web increases significantly, of course, because the web doesn't get thicker with an increase in the height that is given to it through the process of creating the castellated beam. So that's why we don't use castellated beams as columns, or we don't have castellated columns because of that very thing there, because then it's automatically a class 4 section, which adds some additional complexity. So if I check this, I'm just going to take the B value, which is 192.8. I'm going to divide that by 2, and I'm going to divide that furthermore by the thickness of the flanges, and we're at 4.8. 0.91, which means that we're well within our limits. And of course, we're not concerned about the web because that limit is incredibly high at 100.8. But we can check that. So we can say that HW, which is 636.5, and we're going to divide that by 11.4, which gives us a limit of, or a value of 55.83, which is below 100.8. All right, so we're happy with this. I'm going to click on OK, and then I can assign this to both of these members. All right, so now I need to start the process of, or I can decide to add the cutouts. So I'm going to click on AM1, say new operation. I'm going to click on opening. And you can see, if firstly we look at the related plate ID, I want this in the web. And there we have our little cutout. So I'm going to create the diameter, I think around 350 or maybe even 400 should be okay. We can make that slightly bigger. And I'm going to say, let's work with 8 for now. And we're going to say the delta X should be around 700. And that looks decent. So we can add some more there. I think 11 is okay. I'm probably going to keep it to 10 and just shift this guy up over here. All right, so I'm going to keep it like that for now. We can always come back and modify it. So I want to take note of these values. I'm going to click on AM2, new operation and opening. I'm going to set this as the web. And again, I'm going to look at the count is 10. Diameter was 450. The delta, yeah, of course, the delta was around 750. And then our X shift, delta was 700 and X shift is 800. Okay. All right, so far so good. What we need to do now is we have to define our connections actually, and these are based on our nodes. If you want to add additional members, so even if you have those purlins that are running on top of the flange, you have to actually select that particular member and add an intermediate node. Okay, so I'm going to click on connection 1, which is here on the left-hand side, and I'm going to say add related members ended in the Z direction. So Z is vertical, so that's that over there. And I'm going to do the same with connection 3, which is on this side, and Z there. So ended, of course, because these are rafters, so they're not cantilevered in a sense, but if we have to take the rafter away, these columns would be cantilevered, all right? So just the bottom is connected. In the direction, I want to set the height of that column, so -8. You can see that extends there, and I want to add that it is a fully fixed support. I'm going to do the same for the other side. Because otherwise, if we don't have those lateral running members, so whether you want to add eaves or something like that, if we don't have those, the model would actually be unstable. That's why I'm setting these supports to fully fixed. All right, so now we're going to start the process of adding our connection. So I'm going to click on connection 1 and go to edit connection. And this will now open up the IDEA StatiCa connection interface where we can build up our connection and then design it as well if we would want to do that. So here we have a connection. I'm going to check if I actually have a connection predefined. So let's see. Unfortunately, I do not have a predefined connection. So what I'm going to do is I'm just going to build up this connection very quickly. What I might want to do first is to change this section. So let me actually just close this. I'm going to change this to a larger I section or even H section. So let's have a look here. Okay, I'm going to go down to universal beam and let's look at maybe one of our bigger sections. So the 533 by 210 by 92. Let's see what that looks like compared to that beam, and that actually looks quite okay. So the sizes of these members will definitely affect the stability of your model. So just be aware of that as well. These are not arbitrary. These are not just things that look nice. They are actually quite important for your design of these castellated beams. So now I can click on Edit Connection. And I'm going to quickly run through that so that you can also just see what that looks like. All right, so here everything is all good and well. I'm going to click on Operation and Cut. This is something that I've discussed in some of my other content as well. So I'm going to say RM3 cut by, I'm going to say extend member and perpendicular. I don't think this necessarily matters. Let's just see. RM3 is cut by M1. That's good. Let's check minus 500. Yeah, that's all good. Yeah, so depending on the option that you choose, your offset direction might be negative or positive. All right, so this is not a problem. Those plates passing through each other is really not an issue. I'm just going to go for an end plate. And there we go. Okay, so there's our end plate. It puts some geometry in automatically. We can modify that quite easily. So I maybe wanted to just extend a little bit. Let's see. Yeah, that's okay. With the bolts, it can get a bit confusing. So what I do initially is I just zero all of them. I'm going to change my size. I want M24s. And then what I can do is I can start the process of placing these bolts. So top layer, if I check what, or rather left and right layers first. So let's see, minus 35. You can see it brings it in quite nicely. So I'm going to go for minus 40 and then right layers minus 40 as well. So this is just the best way to approach working with the bolts. Otherwise, it does get a bit confusing. Then I'm going to go minus 100 and that seems quite good. And then I can go minus 100 times 2. I can do the same with the bottom layers. And then we can go, oh, that's minus 40. I want minus 100. Oh, sorry, that's my bad. And let's go minus 100 times 2. And it all seems quite decent. All right, I'm going to extend this plate quite a bit. Let's go for around 600 because I want to add a haunch. So I'm going to go Operation and then Widener. It's on member AM1 and it is related to this plate over here. Its location, I just want rear. And I'm going to extend its depth. Let's see. Let's do that by 1,000 and this by 500. All right, that seems all good. I just want to see, yeah, change it to triangular with flange. And then I want to give it the same width, of course, that flange width as this B value, which is 192.8. And then the flange thickness will be 19.6. Okay, so that seems all good. I might make it a little bit shorter. There we go. Okay, so that is all good. There's a reason why that member all of a sudden extends, and that just has to do with how the stress distribution and those sort of things work for members of specific sizes. It is related to the actual height of this member, and that's definitely something to look into a bit more when it comes to working in the IDEA StatiCa space. All right, I'm going to go back to my end plate again. I'm going to extend these bolts. So I have to now create a positive value because these are cumulative. So I have to get from that location of that bolt, so that minus 100, minus 100, minus 100. I need to get now to a positive value of 400, and then I can say again 100 times 2, maybe even times 3. It looks a bit tight in there. Maybe somebody can get a bolt in there. I am not 100% convinced of that, but okay. We're happy with this. This is an absolutely massive connection, but that is an incredibly big beam as well. And I want to put in 3 stiffeners for my column as well. So I'm going to go for my stiffeners. It is on member RM3 and then related not specified. Position is both is fine. I want to set that location as end, and we've got a nice little end plate over there. I'm going to create a copy, and I'm going to say that this is both, and its X position, let's see, 500, 750. 750 seems quite good. That actually seems like it's on the money. Both sides are good. I'm going to create another copy of this one, and I'm going to extend it even further. Okay, that's almost there. Let's make it 1300, maybe a little bit less, so 275. Okay, so there we go. That's our initial connection set up. Of course, I'm not going to design this particular connection in this webinar, but once I hit save, you can close this and you'll see that the member space has now updated with that connections geometry, which is brilliant. I don't have to copy, I don't have to go into connection 3 to do this again. I can say connection 3 and it says recent connections and I can hit apply. Now the last thing I want to do is to look at the apex connection. That's connection 2. Can I rename these? Let's see if I double click on them. No. So unfortunately they are not, I can't rename these connections. They are kept as connection 1, 2 and 3. I'm going to say edit connection. Maybe we have a proposed connection that can work here. Let's have a quick look. All right, so here's our apex. I'm going to go to manage. We do have an apex there, so I'm going to select that guy. Hold on, I'm going to manage. There we go. It should be, oh, there we go, propose. Sorry about that. I'm going to say okay. It's just picking up that there's differences between the two, and I say okay. And I just need to change the position of these wideners to rear. And I can decide to leave it like this, or I can just increase it a little bit. So I might go to my end plate and increase its depth to 600 for these 2 end plates, and then add some additional bolts. So again, I want these as M24s. I might need to bring them in, so minus 40 as before. And let's see, maybe a times 2 here, or even a times 3. Okay, there we go. I'm going to increase the width of these guys. So let's look at 500, maybe 525. And then this guy, I'm going to make a meter. So you see that's too long. 750 works. 900. Okay, 800 works. Then I want to increase the number of bolts here at the bottom as well. So I'm going to say times 2, maybe times 3 again. I'm super skeptical. I don't think that guy there is going to work. So I'm just going to keep it as times 2. Then with this guy, it's 525 and 800. Okay, that all seems good and well. I can of course add stiffness here if I want to, but you can do the same in member. So I'm hoping these work well. So I'm going to hit save. I can close this and we can see that apex over there. I might even shift up these openings. I might have one less. I'll make it 9. And then I'm going to shift these guys up. Let's see, 900. Okay, that's too much. Let's undo that guy. Okay. I think I just changed the wrong one. Okay, there we go. Okay, this is an iterative process from time to time. Okay, delta was, we can make delta 750 now actually. Let's go for 9. And then this guy was 1, 1. Okay, so our model is pretty much complete. However, what we'd want to do is we'd want to add 2 additional operations, and those are for lateral and torsional restraints actually for the top of the flanges, because you'll have purlins running here with cladding on top of them as well. The reason being that if you don't have those lateral restraints, your member buckles to hell and gone. And it isn't realistic because those purlins, because this is now the compression flange with the loads we've assigned, the purlins do actually uh, contribute lateral stiffness or lateral stability to this particular member. So that's why we want that operation. What I did check is, does the addition of the purlins, which one benefits the buckling factor the most? And actually, it's that the purlins benefit the buckling factor the most. Adding these lateral torsional restraint operations are actually results in a more conservative output, which is quite nice actually. So I'm going to add them. I'm keeping them as continuous and the torsional and lateral restraint as rigid. Again, I wouldn't have done it this way if it wasn't for the fact that actually manually modeling those purlins like you saw earlier on, if that would have been less conservative, okay, then I would have actually had a way of fast tracking just the modeling of those purlins. But actually using this operation is more conservative than actually modeling in those purlins. All right, so I'm going to keep this as is for now. So let's just quickly discuss the benefits of castellated beams. Now, castellated beams, the main benefit you get out of them is just their strength to weight ratio. So even though that this originates from a specific type of I-beam, what you get by with this configuration here is actually that the strength to weight ratio increases quite significantly, which means that you can cross larger spans without increasing without the mass increasing of that beam itself, which means that your galvanizing costs are down, your installation costs are most likely down in some way. You do have welding costs, of course, that increase the cost a little bit or that contribute to the cost. But the reality is that this is stronger for exactly the same weight, which is brilliant. There are some additional benefits, more minor benefits. Some of them say that it's aesthetically more pleasing and stuff like that, which maybe we can give them that. But the true benefit lies in the strength to weight ratio of these beams versus the original beams that these were cut from. All right. So we are happy as it is at the moment. We are going to keep these loads as minus 30 kilonewtons per meter. So that's about 3 tons per meter. And what I'll do is I'm going to run my first set of calculations. So I'm going to go and I'm just going to save this and I'm going to start my calculations. So if I go to the check tab, you'll see that there are 3 checks. That's the materially nonlinear analysis, the linear buckling analysis, and the geometric material nonlinear analysis with imperfections. Okay, so that is where the money lies within the context of member and where we benefit from trying to design castellated beams. Okay, so I'm going to run my calculations along. This one should be quite quick, the M&A. But there really is a ton of content on this, and I'd highly recommend actually reading up a bit more on this within the IDEA StatiCa knowledge base. I'd really recommend going there and reading up more about these different analysis types. All right. Now, commonly, how we would simulate or model castellated beams, or at least how I would do it, is with three different plane shells. Okay, so being a plane shell to represent the web, we have all of the cutouts, and two plane shells to represent the top and bottom flange, respectively. That is not a bad way of doing it, but your design is quite limited in that there is a lot that is not taken into consideration in the conventional way of designing these with software. Where it becomes tricky to do by hand, of course, is the fact that you have variations, cross-sectional variations, all along the length of this member. So member, what that does, or the member application, is with the GMNIA analysis, it goes into a very complex analysis space where it can take a lot of these different checks and concerns we have into consideration, even if we had to load this with torsion. Because, of course, all the load effects or all the loads have an equivalent stress and strain effect, and it can take all of those into consideration for us. All right. So firstly, what we see here is we have 100%. That means the analysis has been run successfully. So 100% of the applied loads have been applied. That's very important because, of course, if that value decreases, it means that we have some form of instability in the model. And that can be the resultant of just your support conditions, or in most cases, I would imagine, if your model deflects a lot. So if you have a considerably high deflection. Okay, so 100% is really good. That's what we want. Then M&A plates. This is our um, plastic strain check. All right, so the Eurocodes specify that we can exceed the yield of the material up until 5% plastic strain. Of course, you're not going to design up until 5% plastic strain. You'll probably limit it to maybe 1% or something like that. But this zero point 0.1 here means that we are at 0.1% plastic strain, and we have exceeded the yield of the material at some point in this. So I'm going to click on stress, and we're just going to look for very high stress values. So the stress values that exceed the yield. So there's equivalent stress. It seems like it's in our apex, maybe. All right, maybe at these bolt locations, but there's nowhere where okay, there we go. Okay, so at those end plates, that's most likely where we have exceeded that plastic strain. But we are not done. Okay, so for all intents and purposes, this is just the first check. A very important check is to run the linear buckling analysis and get a buckling factor. All right, so M&A has run successfully. I'm now going to run a linear buckling analysis, and we're going to check the value. Now, that value is going to tell you something very, very important. And that, so also the sequence of this is important because you actually have to run one analysis to continue on with the next. So we're waiting for this value. Okay, we should have it, and there we go. Okay, so 2.1. So this is a buckling factor of 2.1, which is decent actually. That would most likely pass in my books. Okay, so buckling factor of 2.1. Of course, if it's 1 or less, it means that the applied loads are actually causing members to buckle. All right. So now the guidelines for IDEA StatiCa member is that if this value is less than 15, then we have to proceed with the GMNIA, so geometrically and materially nonlinear analysis with imperfections. Okay, that's quite a mouthful. So I'm just going to say the GMN. We have to proceed with the GMN if the local buckling factor, or the linear buckling factor, apologies, not local buckling, the linear buckling factor is less than 15. If it's more than 15, the M&A is sufficient for the design checks. Right. Now, very important. If we have to proceed with the GMN, we have to put in an imperfection amplitude. Now, imperfection amplitude is unfortunately not calculated for you. It's something that you have to calculate. Now, the imperfection amplitude has to do with the type of profile, the buckling axis, so which axis is it buckling about, and so forth and so forth. All right, so this is something that is discussed in the Eurocode, and there is an IDEA StatiCa article that discusses the calculation of this imperfection amplitude. Okay, so the imperfection amplitude is based on a set of tables, and the only problem is that you have to interpret the buckling axis. So which axis is it buckling about? Is it the strong or weak axis? Because that determines the buckling curve. The buckling curve then in turn determines the imperfection amplitude, basically. Okay, so the formula is E0 over L is equal to 1 over 200, because for this particular scenario, I assumed, based on what I can see, that the relevant buckling curve is buckling curve B. Okay, so this is all stuff that is recorded within the Eurocodes. And if we have time, I might even go there and show you where those are. Okay, so I'm going to calculate these. Again, this is more of a complex topic, and it would deserve a webinar on its own, but it's highly theoretical. So if you want more information on this, you're more than welcome to write me an email. So based on what I could see and what I could calculate, the imperfection amplitude is 41 millimeters. All right. Now we can actually proceed with the GMN. Uh, if this passes, we are happy with our design. Okay, then what I'm gonna do is I'm gonna then shift these loads over. Well, I'm gonna shift them over anyway, just for time. But this particular analysis might take a little bit longer to run just because it's a more complex analysis. And therefore it just takes more time. I see Pokemon, you have just posted something in the chat. Yeah, thank you so much. I really appreciate that you like the channel. Um, and you are asking, may you also please consider making more steel design videos for robot structural analysis? Yeah, definitely. I'm definitely keen to actually jump into that again. I did have a bit of a bout where I looked at a lot of robot content, but I'll definitely jump into that again, just to look at steel design and those sort of things. And what's really nice is that robot integrates beautifully with IDEA StatiCa, so I'll definitely look at more of those. So let me just write that down: steel design for robot. Thank you very much. I really appreciate your support. All right, so we see here that we are at 0.1, and it's increased slightly from 0.11, and this means that we are good. Okay, so we are happy. This is a pass in my books, and we would proceed on with the connections. All right, so now what we're going to do is we are going to place these values on the edge. Okay, let's see. We might even remove those lateral torsional restraints. So I'm going to place these guys, I'm going to put them more to the edge. I'm going to narrow their application, maybe to 50 mils. I'm going to increase their size. So I'm going to set these as minus 50. All right, and I am going to move them over. Let's see, 25 mils. Has that moved? Okay, so EZ is most likely not the value. Let's try, let's just see. Okay, so EZ is not the value. Let's try this one. Okay, there we go. Okay, I don't want it like that. Let's do minus 50, and they're all on the same side. Okay, so these are eccentric now. Again, if all of this passes with flying colors, what I'll do is I'll just actually come and remove those lateral torsional restraints. Okay, I'm increasing the size slightly. I do want to pinch this guy a bit. And now we have to proceed through the whole process again. So what I'm trying to do is I'm trying to get to a place of failure and then looking at some of the remedies we have. But sometimes it really is hard actually to push a design to a point of failure. And with that, I do want to say as well that if we see failures in the industry, there's no reason for those to happen. Okay, so here we're at 1.3% plastic strain, which is quite good. Those lateral restraints do help, and they would. All right, so it's more realistic to have them because we would in practice, of course, have those purlins running on that top flange with cladding attached to the purlins as well. But we are at 1.3%, which means we're really pushing. We are pushing this beam. I'm now going to go and proceed with the linear buckling. It should also reduce slightly with that increase. That factor will be lower with that increase in magnitude and also the eccentricity. So we'll see that factor reduce. I think it was 2.1 previously, so we should maybe see it at 1 point something. I'd be surprised if it's actually smaller than 1. I'm hoping it's smaller than 1, but I doubt it. I know that if we remove those lateral restraints, um, it would be significantly lower, but of course it isn't accurate to do it that way. Hey, we're at 1.04. That's good. So we're on the cusp of actually these elements buckling, which is really, really great. I'm going to keep my imperfection amplitude as it is because nothing has changed. And I'm going to proceed straight forward with the GMN analysis. So I'm going to click on calculate. And let's see what happens. So buckling is a really technical topic. Torsion and those sort of things and lateral torsional buckling are not the same thing, and it really takes actually just diving into these sort of things to understand them really well. I do not blame engineers for actually designing torsion out of their models. So basically your geometric arrangement is such that you don't have torsion in your members, which I would highly recommend. But with IDEA StatiCa member, you really can push the limits and design things that have been that previously have been very difficult to design, and especially castellated beams. I do believe that IDEA StatiCa member, if everything passes, I do believe that this will give you a lot more peace of mind than your conventional approaches would have. Now, just importantly, while we're waiting for this to finish, one of the reasons why I checked whether or not the flanges and the webs are class 4 is that member has not been verified for class 4 checks. Now, a class 4 element is an element where the local buckling will happen, or rather where the element would fail in local buckling prior to reaching its yield stress. Okay, so very important. Those checks have not been verified in IDEA StatiCa member, and so therefore it is super important to check the class of your flanges and your web prior to starting with your design, because if it is a class 4, IDEA StatiCa member has not been verified. Okay, all right, so here we're starting to sit with a problem. So you can see there's quite a lot of out of plane deformation, and our applied loads are at 66.8, even though our shear is now at 0.6, but that's because not all of the loads have been applied. So what we're going to start doing now is we're going to try and modify these beams to try and get them to 100%. Time might leave us in a place where we don't get to that, but we are definitely going to try our best. So the first thing I'm going to do is I'm going to add stiffener plates to the web. So I'm going to say new operation, transversal stiffeners. And I'm going to move this guy maybe a bit back. So 600 for now. And I'm going to create a copy I'm going to move this guy up 1200. So I want to get right between those two cutouts. That looks relatively decent. I might just even make that 1450. Okay, so 15 seems to actually be relatively in the middle. Let's make it something along those lines. Okay, got a bit of OCD there, but nonetheless. Okay, I'm going to set it to 8, and our delta, let's look at 1000. Okay, 1000's too much. We go 750, and 750 seems to be good. I'm going to make this 9. I'm going to move that other guy in a bit closer just to keep with the geometry or the spacing, and that looks relatively decent. Okay, I'm going to go to AM2, add a new operation, a transverse stiffener. Oh yes, and like I mentioned, remember I mentioned the node orientation before when you are creating your model? If I set the nodes the other way around, this stiffener would be starting at that end, which is confusing, right? Whereas now they're both starting from the same end, which means I can match their values quite easily. So I don't have to figure this out from scratch. I'm going to create a copy. I'm going to see where does the stiffness start. It's at 1475. Then I'm going to set a repeat count. I think it was 8 or 9. Let's see. It's 9 and then 750. Okay, perfect. Okay, we've got that going for us. And what we might do as well, we could even add a stiffening plate to the top flange. All right, so I'm going to do that. That is just a bit more of a finicky operation. I don't like doing that necessarily. But okay, we've got this plate. If I make it 0, you see it is a bit, it could be a widener. There we go. Okay, a widener is better. Let's see. Okay. Its X position is unfortunately in the other direction. So that doesn't help us a lot. And that position is not ideal. Okay, so X position, if I do this as 1000, you'll see it moves it, and I can't move it in the Y position. All right, so that doesn't work. So a rib is unfortunately the one you have to work with. Okay, so you set it to one side. We say pitch is like that, and then rotation is like that. Okay, not the best workflow, but it does work. All right, you can see that guy is on top, not quite. Let's see. Okay, I want to extend that guy. I'm going to say no weld for now. And then I want to set its width, let's say to 400. And its Y position. Yeah, so it works something like that, unfortunately. Okay, let's see. Okay, we can then assign the weld, so I might have to make that slightly wider, so thank you for just bearing with me. Okay, width, and let's do 150. And let's see. Okay. Oh yes, I need to rotate it. So 0. Trying to think what I did the previous time. So apologies for this. This thing is a bit of a problem. To place. It doesn't always work the best. I think what I have done previously is actually just to, let's see, okay, the pitch there. Let's do a doubler. I think a doubler was the right one, I must admit. Again, the doubler sits there at the bottom, which is quite annoying. Okay, I might not actually just try this. I might not run with this. The problem is that that guy, let's see, both sides, that guy sits like that. Okay, which is not something I want. So I might just exclude this for now. Let's just, for the sake of running the analysis, let's work with these guys for now. I'll get to running with that that plate. It just takes a bit of experimentation. Something I've done previously, where I've looked at actually assigning or creating that a flange thickener, basically, so to thicken the flange of the beam. It's just, I'm trying to think whether or not it required an operation. I don't think it required an additional operation. There was just a way of playing around with its orientation that was important. Okay, let's proceed. So I'm going to go for my LBA. And we'll see an increase. So remember, previously it was like 1.02, 1.04. So we need to see now if anything has changed. If it hasn't changed, then it means that our stiffeners are not really helping in what we are trying to achieve based on the loads we have applied. Okay, we're almost there. Unfortunately, with this being live, that is just the way it goes. But then you can also see how things are happening in real time. And 1.25, so that means that we have had an increase in buckling resistance. And then we might have to run, let's run the GMN quickly. Unfortunately, this does take a bit of time. So we might find ourselves in a position again where the applied loads are not at 100% because the stiffeners are not sufficient. But then we will try our very best to get that plate on the bottom flange of the eye section. Actually, we'll try our very, very best and then run the analysis one more time. So really hoping we get to that before our time runs out. Luckily for those, if you have to go, if you're watching this in your lunchtime, our webinars are recorded. If you miss the last section for any reason, you can always come back and have a look at the last section. Okay, so hopefully this load 100% is a good sign. Sometimes this little screen here is a bit misleading, but I really do hope that that we are getting to where we need to be. Of course, IDEA StatiCa member isn't it isn't foolproof at the moment, in that the imposed loads that you apply on the members, although you can check what the generated load effects are, it doesn't transfer those load effects to your connections, which is something that I really hope for. It's something that I've actually spoken to IDEA StatiCa about, and it seems like that is in the pipeline. So what that would mean is that you would design your members based on the imposed loads. Those loads would then, of course, have load effects. That would be the axial forces, it would be bending moments, etc. And those would transfer into your connections. At the moment, it isn't. You actually have to go and create those load effects in your connection. And that's where it's useful to partner or to work with or to have an FEA package on the side, like Sumo or Robot, that you're working in, so you can actually see what those load effects are. Of course, IDEA StatiCa's checkbot works incredibly well for this very reason. in that it transfers those load effects to the connection, or it records what those load effects are. So I do think this analysis is struggling a bit. The fact that I do not think that we are going to get 100% of our loads applied, which is quite a bummer. That's why it is running so long. Like it's actually trying to apply those loads. I think we're going to set it about 75. Yeah, 75%. So we're getting there slowly but surely. So you can see that there has been an improvement based on adding the stiffness. So I'm going to try one more time just to add those plates in the bottom, and then we are going to run out of time, unfortunately. Okay, so let's look at transverse stiffener, and I'm really hoping I get this right quite quickly. So let's just put that on the bottom flange. I'm going to rotate it. It is at 0. It should be, I do think it remains a rib, to be honest with you. Let's see, rather 90 and 90. I think what has to happen is that it should only be 1. And it's strange that it works like this, because it should technically be on the bottom flange. Let's see the left side. Okay. Let's see. Pitch. I think I need to play around with the pitch a bit. Let's look. Oh, I think this was it. I think this was the ticket. Okay. So lengthwise, if I make that 100, okay, that's the length. And the width, I think that was that how we did it last time? I think it was like this, playing with the thickness and the width values, if I remember correctly. I'm just trying to see, where is this guy now? Okay, there we go. Okay, so I'm going to move this guy up even further. I want it outside of the haunch. I do believe that this was how it was done. Although it's just being welded on the one side, which I don't think that's correct. But you can see that we are getting there. So let's go for a thickness of 10. Rotation, let's do that rotation seems good. Okay, that's not it. Its length can be 1500, like that. But its width should be in a separate direction. So if I change this rotation, I make it 0. And I make the pitch 90. Yeah, it's not welding in the right location. Okay, so we'll do it like that. Let's see. This is sort of where we should be. Let's see both sides. No, that's top and bottom. That's fine. We have a doubler. Let's see. Okay, the doubler is good. Okay, there it is. I think that's it. I think we've got it. Let's see, 150. Okay. So I'll make this like this. The length should be, let's do 300. Okay, and then the Y position should be half that. Something like this. Let's do the fillet front side. That looks great. And then the length, this should be that value. There we go. Finally, as you can see, that is such a flippin' pain to do. Oh my goodness. It's really not that intuitive when it comes to doing something like this. I really wish it was. Okay, there we go. So we have that plate. We're going to put it, I'm going to make this guy maybe 15 mils thick, just so that the welds, I want a weld of maybe 8 mils. Let's see. And then I'm going to put in the same plate on the other side. We'll see whether or not this um, has a significant enough effect. Okay, so let's go for new operation, transverse. I'm going to, of course, copy that guy. So bottom flange thickness should be 15. Okay, it should be a doubler. All right, then location is right side or left side, actually, it doesn't matter. Let's do left side. X position should be 1, 5. Okay, I'm just going to record these values quickly. 1, 5, 150, 300, 5 to 50, and then there's a 90% rotation. Okay, cool. So we don't have to come back the whole time. All right, so 1,500. The Y position is 150. The length is 300. The width is 5 to 50. And that should be it. Okay, and then this should be on the right side. Let's just see. That looks good. Our weld is front side only, and it should be an 8mm weld. Let's just confirm that for both, an 8mm weld. Okay. All right, so this is going to be the last check that we run. We're at an hour. So I want to save this, run this, and we're going to see how this is going to end. So I'm going to go into my check space. I'm going to calculate. Wait, did it say, did it mess with something now? Oh, okay, let's just see quickly. Let's just have a quick look. Yeah, okay, the calculation was interrupted. I just want to see, doesn't seem like anything went wrong there. Okay, all right. All right, this is our last check. Hopefully this works. Otherwise, we unfortunately have to conclude on quite a sad note. Okay, come on. Just give me 100% with the M&A, then at least it means that our stiffener plate has been modeled correctly, which is what we really are hoping for. Because then once there, we can proceed with our LBA. Ooh, that looks good. Come on, give me 100%. Yes. Okay. Brilliant. 100%. That is amazing. I am really, really happy with that. That means the stiffener plate is contributing to this member's stiffness and so forth and load bearing capacity. Our M&A is at 1%, so we're at 1% plastic strain. We now have to go for our linear buckling analysis. So I'm going to run that guy. We're going to see, we're expecting an increase. So hopefully we are at about like 1.5 or something. And then we're going to run our GMN and check what happens. Okay, come on. Let's get through the linear buckling analysis. Of course, the GMN is going to take even longer. So thank you. Yeah, just thank you for your patience and sticking it out. I really do appreciate it. Okay, 1.26, so not a massive improvement actually. All right, let's run our GMN and see what happens. And while we're running the GMN, I can just actually conclude with saying that what you'll notice is that I have a ton of room to modify this member, modify its connections, and so forth. And that's really what sets IDEA StatiCa apart, in that I can try a multitude of configurations. I can weld additional plates on. I can play with that welding. I can change the size of connections, all of those sort of things. And I can really test this up until the utmost before I look at increasing the size of the main members. And so that's really, really something to take into consideration, is that IDEA StatiCa makes it possible for you to try out modifications that aren't possible in normal or the standard FEA packages. There isn't a package where you can comfortably model, or wait, hold on. Let me rephrase that. There isn't a package that we use that where you can comfortably model all of these stiffening plates, change their position, cut holes in them, you name it. There isn't. We don't have that functionality readily available in other software packages. And so I'd really recommend, if you haven't ever tested out IDEA StatiCa connection, or even the member module, even some of the concrete modules, that you really, really do take the time to test them out. In the event where you sit in a situation like this, where you really need to get something to pass for whatever limitation you might have, whether that's access to material, whatever it might be, IDEA StatiCa is going to give you the best shot at seeing whether or not you can make it work with the addition of plates, modification of members, and so forth. Right, I can see that the iteration is jumping a bit. It jumped to 100%. Now it's at 81.25. Now it's at 78.12. So maybe we won't reach that 100% that we were looking for, which I'll be really bummed about. But it will still demonstrate the workflow. So the intention of the webinar has at least been met. I'd of course love to hear from you. So if you want access to these kind of models, if you want to see whether or not you can make this particular model work with some additional modifications without increasing the size of your members, I'd be more than happy to actually share the folder with you. Of course, you do need access to IDEA StatiCa member to do that. So if you haven't used your trial already, then maybe think of using your trial, playing around with it, and you'll really see the strength of the program once you start having to make these small little tweaks and things like that. So, of course, reach out to me via email, put something in the chat. You're more than welcome to. I think, we're at 78.1%. So, unfortunately, we just could not get our GMN to run at 100%, which of course means that this check is not finished. Man, what a bummer. I'm so sad to end on such a note there. I'm going to save this. I'll probably look at putting out some content where I see if I can make this work. But other than that, I really appreciate your time. Thank you so much for watching. Please look out for our future webinars. They will be announced in due course, and it will be around similar topics and things like that. So thank you very much. I hope that you have an awesome afternoon further. Please subscribe to the channel, hit that notification bell so that you are kept in the loop. We also have a ton of Autodesk content that we actually post vlogs on. We have a ton of Procon content as well, and they are all available for free, of course. Interact with the chats on the Procon IDEA StatiCa stuff. I do make a point of looking out for those comments and responding to them. Have an awesome afternoon further, and I'll see you in some of our future